In this video, we're going to talk about minimization of Boolean logic circuits using K-maps, also known as Karnaugh maps. So you're going to see things that will remind you of the symbolic logic that we've studied in this course. So as a reminder of how things work in Boolean algebra, the plus sign or addition means or, times, which will usually be represented by a dot, or possibly just writing two letters next to each other, is going to mean and. Complement is shown by a bar over an expression, and that means not. 0 means false, 1 means true. This is a reminder of what the logic gates are going to look like in this video, and they are paired with their name, what the gate looks like, and their truth table, plus different ways you might see Boolean notation indicated. We're not really going to use the NOR, NAND, and exclusive OR gates, but they're there for your information. The main question we want to answer with all that background information is, how do we take a complicated Boolean logic circuit and simplify it so we have fewer gates but we still get the same output? For example, let's say we have this logic circuit here. We have a few NOT gates, we have these three AND gates, and those AND gates are leading to a single OR gate. Is there a way to make a simpler circuit diagram that will produce the same output? To help us answer this question, we need to know some properties of Boolean algebra, but before we even do that, we should write this circuit diagram as a Boolean expression. And so this first AND gate is going to be three things multiplied together, because remember, AND means times in the Boolean world. And before we multiply these three things together, we have to negate one of them, in particular the z. So we're going to go ahead and do that. So we have our Boolean expression. It's going to be x, y, z bar, which reading it in logic terms is x and y and not z. Then we're going to take a look at this next AND gate. And we're going to have x, y, and z again, but this time both the y and the z are negated. And since this AND gate cluster is connected with this AND gate cluster at this OR gate, we're going to connect these with a plus sign. So plus my second gate, AND gate, which would be x and not y and not z. And finally we have this third AND gate, which is just x and z. So we'll do plus x and z. Again, if we want to simplify this, we need to use some properties of Boolean algebra. So we're going to take a look at those right now. These are some of the Boolean algebra properties, and we're going to focus on certain ones. Notice that some of these are very reminiscent of just regular algebra. For example, anything plus 0 is that thing. Anything times 1 is that thing. But remember, these are logic statements. So this is saying x or false is x. X and true is true. We have commutative laws, we have associative laws, we have distributive laws. We also have these domination laws, double complement law, idempotent laws. We won't use those that much here. Distributive property and associative property. And then we have De Morgan's laws, which are interesting to just know. The absorption laws are also interesting, but we're probably not going to use those too much here either. The main one we're going to use is going to be this unit property. So we're going to use unit property. Okay, so just to sum up, we're going to use the unit property, the distributive law, unit property, distributive law, identity law, and probably commutative and associative laws in the background. This is the Boolean expression that we derived from the circuit diagram we drew earlier. So we're going to use those properties right now to try to simplify this as much as possible. One thing I notice is that these two terms, the first two terms, are exactly the same, except one has a y and one has a not y. So I'm going to factor everything else out using the distributive property, which means I'm going to have x z bar times y plus y bar. And then I'll just copy the plus xz. So what I used here was the distributive property, and technically also the commutative property, and maybe associative property. Those often operate a lot in the background. Next, I'm going to notice that the y plus y bar, y or not y, is true, which means everything in parentheses here is going to turn into a 1. So I'm going to have x z bar times 1 plus xz, and that was called the unit property. And then anything times 1 is just that thing, which means that's going to give us xz bar plus xz, so that's the identity property. And then now, what else do we notice that's in common between these two terms that we have left? Well, we have x in common, which means we can factor that out using the distributive property. And so we have x times the quantity z bar plus z. In other words, x and not z or z. So this is distributive property. And in a way similar to what we did with the y plus not y, we're going to do a similar thing with the z bar plus z. So we have that will become a 1, and then x times 1 is just going to be x. So that, again, this will be unit property and then identity. And so what that tells us is that complicated diagram from earlier will now become nothing more than just x. And what does that look like as a circuit diagram? It's just x. Sometimes people put a triangle with no little circle at the end of it to be a buffer, because that's all there is to it. It's just that one variable. So we were able to use properties with this particular example to simplify it and make the circuit diagram a lot smaller. But sometimes it's not as straightforward as this to make that simplification. Sometimes you want a different way.